Flutube. Get it straight.
Okay, now we're going to look at part 2 for chapter 6. And we're going to look at conservation of mass or continuity and see how this connects nicely to the streamline function. And this is streamlines are what we talked about earlier. This is a slightly different but very similar concept called streamline functions, where we actually have an explicit function for the streamlines. So you'll see how it matches up with what we said before. So remember the continuity or conservation of mass equation that we did in chapter 5. It said that the mass in the system would not change over time, so the total derivative of that Reynolds transport equation here's would equal to 0, and so here it is in terms of the Reynolds transport equation. Again, this is for a control volume look, so mainly for bigger things or macroscopic view, we like to say. So if we look at first, let's just look at this first control volume term. Differential form, we'd say the change in time of the integral of rho dv is the Reynolds transport formula. That's basically in a small cube equal to d rho dt times the volume of the cube. It's basically mainly looking at this part here and taking the derivative where the volume is just dx dy dz. Now, if we look at what's coming in and out, in other words, if we sort of treat this cube like a control volume, our ins and out terms would basically be these u on one side and u plus du dx on the other side. Just carrying the rho around along for the ride here for a while. So we have these ins and out terms where we have the far side and we have the near side. It's basically the rho times u in the middle here. Here's the near side coming in, far side coming out. So in the x direction, the net rate of flow in the x direction is coming in minus going out, and that's equal to d rho u dx times, again, this volume dx dy dz. We had this, went through the same thing going in this direction and in this direction, so the y and z components, we would get similar terms in y and z directions. So if we put that all together, we would get that the accumulation term is equal to this in and out term in the x, y, z direction. Or we could bring that over to the all over to the left-hand side. You have the accumulation term and the ins and out terms here, all summing to 0. Now this is the del dot rho v. You can see by the dx, dy, dz terms. And if we recall that for steady flow, the local term goes to 0. The change with respect to time goes to 0 for a steady situation. That just says that the del dot rho v is equal to 0. So the gradient of the velocity times mass, the momentum term, velocity of the momentum term equals 0. So how does this relate to stream functions? Well, stream functions enable one to write a two-dimensional velocity field as a single function. So instead of having separate functions for the u and v components, you just get one component for the stream function, and we refer to that stream function using the psi variable here. So this was really helpful for drawing flow patterns. It's very similar to the way we drew streamlines before. You'll see in a moment. This is a little bit more formal. So flows can be estimated also by differences differences between the streamlines. So that's a little bit added bonus that we didn't have to worry about before or didn't use before. So let's consider incompressible steady planar flow. So two-dimensional, so get rid of those z terms. We basically have that continuity term that we had before. I pulled out the rho here from these terms because if it's incompressible, then rho is constant. And in fact, if it's incompressible, you pull out a constant, you can cross it out on both sides effectively, and all you have are these gradient terms. So the two velocities here have a relationship that's called the stream function. And it says that u is the derivative of the stream function with respect to y, and v is the negative of the derivative of the stream function with respect to x. So if you substitute those in for the continuity equation, which is here again, put in the d psi dy for u, d psi dx for v, putting in a negative sign for this negative here, then you get 0 is equal to d squared psi dx dy times d squared psi dy dx. So let's look at an example here. Maybe go back also and look at how you would have done this if I had just talked about the streamlines. So here we have the u component and the v component of a two-dimensional steady velocity field incompressible, so we don't have to worry about the rho term. We want to know what the stream function looks like and sketch some of the streamlines on the plot. So from the definition of the stream function, u is the first derivative of the stream function with respect to y, and it's equal to 2y. Similarly, v is equal to 4x. So if we integrate these in order to get the stream function, we get that it's a function of y squared plus an f of x. So we have to get that constant of integration, but in this case we have to consider that that constant of integration might be a function of x, because if we take a derivative of a function of only of x with respect to y, we'll get a 0. Similarly, we have to put in our constant of integration as a function of y potentially when we do this integral with respect to x to get to minus 2x squared. So the overall stream function must satisfy both of these. So if we add them together, then we can just say a constant, because we've already taken care of the x and y terms here and here. They take care of each other. So it's a little strange, but it works out that when we do these derivatives here and here, everything works out. We have this function of y and x and a constant. Again, these constants are important because they give us a family of curves. So here's the solution. For the actual value of psi does not need to be known. The constant of integration can be ignored for the moment. But by selecting values of streamlines of psi, the streamlines can be drawn. So for example, for psi equals 0, we get y is equal to a line here. So we get these lines that just crisscross over the middle here. For other values of psi, you get 1, etc. You end up with more of these hyperbola type expressions. Remember these arrows that we get by going back to the original u and v problem, u and v in the problem. So back here, go back to these expressions, and they would tell us which way the arrows were going by finding out in which quadrant they're positive and negative. So streamlines are everywhere tangent to the velocity vector, so that's important. And recall that when we first looked at streamlines, we knew that dy dx is equal to v over u. So similarly, along a stream value function, dy dx is equal to v over u. So stream functions, like streamlines, enable one to visualize 2D planar flow. But, as we'll see, stream functions also enable you to estimate flow. You do this by knowing the flow on one line, or knowing the value at one line, you can subtract the value of the other line. So if I know that if this was, for example, psi equals 1, then this streamline minus this streamline would equal 1. And whatever the units are, you could figure out what the flow was, 1 something meters cubed per second, cubic feet per second. Depends on what the units the problem is in. We'll do more of that more later, as we say. I know I kind of threw that out there really quick right now. So let's now look at conservation of momentum. This should actually say part 3. We'll back to the next part.